it's always great to have you here, Paul, with us. It's always inspiring. And yeah, he already showed me a few of the slides this morning, and there are actually a few slides in there which I don't know about the history. So I look very forward to the talk, and then he also will talk a little bit about the future of Melt Electrospinning. So let's welcome Paul in the usual manner.
Yeah, it's great to be back here again. And actually, I think the first thing I do before I start my talk is to really express appreciation for both the Australian government and the European government for actively and encouraging collaboration across countries, across the world. And actually wouldn't be without, I mean, this is the Biofab Master's degree in many, many different ways has really helped enhance the relationship between the University of Würzburg and also University of Wollongong and also Queensland University of Technology. So today is actually a little bit more like a summary, like a literature review, because I know that in today's world we have so many things that we have to do as students. You're coming into new projects and there's all this information on topics such as electrospinning and processing, and as you go through the literature, it's just this bombardment of information. So what I'd like to do is actually go through a little bit about the development of melt electrospinning, melt electrowriting, and also solution electrospinning, just to kind of fill in a lot of the gaps that maybe people are not so aware of, and also to see how fields develop and evolve. So this is a SEM image of a 50 micron box scaffold that we made in Würzburg. Martin Yusuf has made this, and this is really pushing the limits of the technology. We have fibres that are quite close together and also have quite a few layers, and so this is really kind of the limit of making these perfect scaffolds. That was I think this summer. If we go back now to 2004, this is what we're making with melt electrospinning. Okay, slight difference. We were getting a mixture of these small diameter solid fibres, which we were really excited about, these large molten fibres, and then these little particles. And so a lot of the time we spent early on is just trying to work out, well, it's possible to make these fibres. How do we get that happening all the time? And I was really kind of driven to keep working on this, even though this was the result and it's not particularly impressive. From a sort of philosophical point of view, being able to really work with things that can be translated, and actually just started off as a bit of a challenge thrown down by Martin Müller, who's the director of DWI at the time in Aachen. What he wanted to do was actually directly electrospin onto cells. And his approach was to have a micelle solution, and so I was given all these block copolymers of polyethylene oxide and polycaprolactone to put into a solution. And what happens with a lot of these block copolymers is they actually have these phase transitions. So as you change the water content, they can switch from micelles into cylinders, vesicles, and lamella. So the idea was to have at the top, in here, have like micelle solutions and vesicle solutions, so that this will actually flow very easily. And then as we get solvent evaporation, you actually get lamella-like structures, and then you can electrospin onto cells. And this is technically really challenging, because if you use a lot of the solvents that are normally being used that aren't water, they're volatile and they usually have some toxicity associated with them. If it's aqueous polymer solutions, if it's not cross-linked by the time it hits the cells, it'll just dissolve again. And it was incredibly tough, actually. It didn't work. I was kind of persisting for months and months trying to get this transition to work. And I still remember a conversation I had with Ahmed Moran one evening, sort of staying back, sort of talking about, oh, this isn't working, etc., and having conversations with a colleague. And then suddenly it was like, well, what's the melting point of PCL? And I was like, well, 60, and also polyethylene oxide, 60. And I thought, well, that's not too far away from cells. And that really sort of crystallized that thing. Well, let's head in this direction and let's try it out. And actually the first prints, I couldn't find any images of them. They were even worse than the one that I showed you. Literally every sample was just a molten mess, except in one corner of one sample there was beautiful little fibres, and that was it. Honed in on that and kept working away. And the reason I was really keen to work on this is also from my previous experience during my PhD in Perth, where I was involved in the artificial cornea project, and this is one of the first recipient. Actually, this is the first recipient. This is my PhD supervisor, Trine Carrillo, who's now at Queensland Eye Institute, and Professor Ian Constable and Jeff Crawford, who's the operating surgeon. So Ian Constable was the director of the institute. And basically, I worked in this sort of clinically translating project where the only solvent we used was water. And I had this kind of appreciation that, you know, if we want to, actually when I started at Lions Eye, I also want to say there were 3 people in the lab, and we're just starting some animal studies. And when I finished, there were about 15 people, and we're actually implanting into humans multiple times. It was my job to be in the clean room. So I kind of appreciated that the stuff that we do here now can impact people. And if you do university research in a certain way, looking ahead, that you can actually translate this through, but the way that you make it is important. And so I was quite interested in melt processing, even though I hadn't done anything before on this topic, because there is already a path that's been trod by others to make clinical biomaterials for implantation. So just to kind of go back a little bit and talk about electrospinning and the whole basis of it. You know, this was starting in 2002, and actually at the time, electrospinning was a really emerging area. It's a very, very simple process. You apply a high voltage to a polymer solution, and the charge aggregates at this outer part of the tip to the point where you get this jet that's ejected. And the charges increase along the length of the jet to the point where they actually repel each other, and the smaller fibers are made this way. This kind of mat is what you get of these chaotic fibers, and actually gives you something that you can pick up and handle in a very short time, 10-15 minutes. You can make these kind of fabrics. But it's very old. Yeah, this is not a new technology, and actually historically, electrostatics has been studied since the 1600s. So this is very, very old. But the first patents on electrospinning by Cooley in 1900, and also Formals in 1934, and then this was an interesting way of making fibres. And so there's a lot of patent literature, but it never really caught off industrially just because of the output wasn't high enough. Melt processing through melt spinning, coagulation spinning, this really won out in the whole textile manufacturing. And so other than a few, you know, this is a kind of patent where you're kind of trying to make fibres, turn them into yarns. There's actually a very famous and prolific researcher, Geoffrey Taylor, and this is a paper in 1969 where he sort of studied the basic physics of applying high voltages to fluids, including electrospinning systems. And so you might hear about the Taylor cone as you're doing electrospinning, and this is named after this man. I think he died a couple of years after this publication. But really nothing happened in the electrospinning in the research area until 1995. And in that time, though, there was a lot of work being done actually for filtration masks in Russia in case of nuclear fallout. This was under wraps, and so this developed through the 50s and 60s. But there was nothing really published about this because this was a secret. And also some companies started using electrospinning for high-performance filtration systems. But in 1995, this paper was published by Darryl Renniker, and really showing that you can very easily make submicron fibers. This is not a well-known journal, but this paper was cited 3,200 times since. At the same time, or similar time, basically making nanometer fibers produced by electrospinning. This is cited 3,600 times. So this was a person, Darryl Renniker, who's known as the father of modern day electrospinning, and he really kick-started this because this is a period as well where people were interested in nanotechnology. And even though nanotechnology is defined as like 150 microns and below, where you start seeing some quantum effects of the materials that you're making, Darryl Renniker, was making submicron fibers, and that was enough for people to say these are nanofibers. And so there's a lot of interest in this. Mainly for a few reasons. You made these small fibers. It's incredibly inexpensive to set up and simple, and you can actually handle your samples afterwards. And the other thing is, because of all the previous patents on electrospinning, you were free to use this, and there was no kind of patent put onto this that actually affected this survey. And so if you look at sort of the trends of electrospinning, these are the countries that are involved. And what I really like about electrospinning is that it's accessible to everyone in the world. So these are the top countries, including Thailand. China is the major patenting country. And so it wasn't a technology that required a lot of money. And so this made it very accessible to many people. And if you have a look at the patents, tissue engineering is another. This is up to 2015. Tissue engineering has the most patents and journal articles involved in the topic. And there's other applications: drug delivery, wound dressing. And as you look at the evolution of the number of publications in electrospinning, you can see it's increasing continually, mainly driven by tissue engineering, but also other areas. So black is tissue engineering, you can see it increase here. Wound dressings appeared, but then they've sort of diminished a little bit off, maybe a bit more towards tissue engineering approaches. And so there's different applications as well, also fuel cells, and drug delivery is increasing in its use. One of the important papers earlier in electrospinning was this electrospinning of collagen nanofibers. These actually were nanofibers. I think they're about 100 nanometers in size. And you could electrospin this from hexafluoroisopropanol, HFIP. And this made nice fibers, and actually under the TM you can see you actually have sort of the units, the repeat units of collagen. And so this started people thinking, wow, we can actually start like electrospinning ECM. And if you have a look at simulators, the structure around a cell, you have these collagen fibrils that are connected through fibronectin integrin binding sites and actin to cells. And so people were thinking, well, electrospinning makes small fibers, collagen fibers, so it can behave like an ECM. But I think one of the things that was kind of missed a little bit early on is that kind of, it has a similar size, but the density is completely different. So very early on, if you really look at these substrates that are made, the cells are just sitting on top of the electrospun fibers. There's not much space between the fibers for cells to grow and penetrate. But that didn't stop people from saying that these are cell-invasive scaffolds. Even if part of a cell could get into the membrane, then they would say this is cell invasion. I would disagree. Dima would disagree as well. And so this differential between the collagen in the natural ECM and the fibers that we're producing by electrospinning kind of wasn't really talked about until I think Tony Mikos and colleagues was really looking at what happens when you get fibers of different diameters and randomly just deposit them upon each other. If you have a 2-micron diameter fiber, then the pore size, if you just have random deposition, is about 10 microns. And it wasn't until you got to about 4 microns that you started getting 20 micron size pores, just to kind of, and this is actually also a highly cited article. And so you can see that the pore size with the small fibers versus the larger ones are much larger. There's much more pore size in here. However, for people working in electrospinning, this is not good news, because this is not nano anymore. And I've had people say to me, oh, your fibers are 3 microns, that's not interesting because it's not nano. Yeah? And which is actually kind of crazy, because it doesn't, I'm sure cells don't subscribe to the SI unit system, and they disagree whether, I'll invade the scaffold because it's not nano, etc. But the important thing is you still have high surface area. You still allow cells to actually penetrate this time, and they showed this in this instance. We actually seen cells penetrate into them, and these are just randomly deposited fibers. And this is a very important paper to talk about. And I think in general, both additive manufacturing and this is not working. And electrospinning they separately developed in the 2000s. And so people would combine the two, where you'd actually do your direct writing using fused deposition modeling, and then you'd electrospin on there, and you create these kind of scaffolds that have large pores, volume, as well as a diffuse amount of fibers, electrospun fibers in there. And this is a little bit where Dietmar also had, actually, I think you were the first person to use additive manufacturing in tissue engineering. Maybe you can correct me if I'm wrong, but you know, this is very early on. Dietmar was investigating using this melt extrusion to make orderly defined scaffolds, and this is a phenomenally well-cited paper because really this is putting this concept of additive manufacturing out well before 3D printing was just talked about in the popular media. Getting back to these fibers and also why actually Dietmar and I could see similar, sort of have similar concepts on this. I bring together this really interesting review by Scott Hollister, where he describes something called the Valley of Death. And on the left in the blue, you have a lot of the university-based research. And it's relatively well funded. We could disagree, but it does give you the room for freedom to look into sort of different concepts. You can do basic in vitro research and some of the small animal models and so forth. And you have different funding agencies. This is directed towards the US. On the other side, in green, you have industry. And so you have things that are important here, such as the regulatory approval, and you have these products. And again, you could argue, you could say that there's a lot of funding available, a lot of money in this part. Now in the middle is something called the Valley of Death. And this is where a period in time where if you have an idea or a concept here at this sort of basic level, to be able to translate this through to acceptance by an industry, and you have a limited amount of time, a limited amount of money, and you have to demonstrate biological efficacy. And so here you have to be working with some of the larger animals, manufacturing things under GMP conditions and so forth. And this is a tough area. And I, by working at the Lion's Eye, I had experience working in this Valley of Death, and we were able to translate a product to something that's implanted in humans, because the solvents we used was water-based. We'd used monomers that had been used in humans in the past as polymers. And actually, similarly, Dietmar had also gone through this process with the scaffolds and osteopore in Singapore. And so, if you look at melt process devices, there are sutures, there's hernia meshes, bone screws, and this is a really known, effective way of manufacturing a medical biomaterial. Similarly with the micro extrusion, and this is an advanced example of how you can have a look at a defect, Calvario scale defect, and then you can create a scaffold that will fit in place. And so the concept of melt processing, both I was interested based on melt electrospinning and also Dietmar. And this is when we actually met, 2004 in Prague, and this is well before we were doing any melt direct writing. And we could understand that step of being able to go to clinically translate and doing the research at the university level. And actually we collaborated and we worked together without doing any direct writing, but just the fact that I was interested in melt electrospinning, and Dietmar, I'll talk a little bit about that later, but basically, it wasn't the 3D printing that actually brought us together. It was our similar philosophy on how you clinically translate biomaterials from the university. So now if we go back to the melt electrospinning literature, I wasn't the first at all. There was a series of papers in 1981 which actually are now well cited, but at the time they weren't. And actually what's interesting reading them, this is the only paper where they do melt electrospinning, and the rest of these are sort of theoretical papers and actually using silicone oil as a model as well. So there's really one paper in 1981, and then in 2003, Daryl Renneker again, who was doing a lot of electrospinning at the time, solution electrospinning, was working with melt electrospinning of polypropylene, and he was doing it in a vacuum. He was doing it in a vacuum because he was interested in working in space and actually using melt electrospinning as a tool for fabricating structures in space vacuums. This was the only paper that came out. I think it was a little bit harder than solution electrospinning, and so I think they kind of moved on from that project. And actually, even at that time, I remember talking to people in 2005, 2006 about melt electrospinning. I think Clemens van Blitterswyk. And they were saying, yeah, we tried doing some melt electrospinning, but it wasn't making the fibers that we wanted, and so then we switched back to solution electrospinning. And I think a lot of labs did that. I think people knew about melt electrospinning, they tried it, and then they got a mess, and then went, okay, forget about it, let's go back to something that makes nice fibers easily. There's another important paper by Frank Koh's group, also understanding some of the processing parameters of melt electrospinning. And I think also a good example maybe why not to call papers part 1, part 2, part 3 until you've written them all, because there was never a part 2. There was just a part 1, and that's the end of that. But still, nicely cited paper, because it was one of the first. And in this instance, they had applied the high voltage to the collector, and they actually fed in the polymer. And actually, with these kind of extrusion-based systems, the flow rate is high, even though we didn't know about it at the time. That low flow rates are really important from getting nice fibers from melt electrospinning. This was a little bit, I mean, they were not electrospinning really nice fibers, but they were okay. The average diameter was quite large. So here, almost 500 microns, 11 microns, 7 microns. These are the smallest with 3.5 microns, 21 and 13. And this paper literally stuck in the minds of everyone involved in electrospinning. Solution electrospinning, small fibers, melt electrospinning, large fibers. And that's the end of this, and that's basically the mindset within the electrospinning community through the 2000s. That even though there were papers later showing submicron fibers made with melt electrospinning, there was this general feeling that big fibers, melt electrospinning, bad, solution electrospinning, small fibers, like collagen, like ECM, good. And then it just kind of followed that path. I had a lot of conversations with people on this. So back to this kind of mess that we got. We tried to characterize it a little bit and work out, even though we're getting a spectrum of different materials, we tried to characterize a little bit between the solid fibers, the ones in black that we wanted, and we could see that one of the parameters that was important was the flow rate. That, you know, if you were to use a milliliter per hour to spin onto cells, it was a really awful, messy experiment. The quality of the fibers was bad. We didn't have the facilities at DWI to really do this well, but we still tried to do it. And so we were getting Petri dishes and taking out of the cell culture fluid, running down the corridor, putting it into the chemical fume hoods and actually doing electrospinning. And that's where I found out if you have enough antibiotics in your media, particularly fibroblasts, they don't, you know, you can push the boundaries of sterility. But yeah, we could actually see, and also the fiber deposition was really bad because fibers didn't want to electrospin onto Petri dishes. But this is something I think is interesting, and we'll probably pick up again in the years to come as we sort of do more and more work on this topic. One of the things, and this is now 2007, I noticed when we were having certain formulations, you could get these really, really long jets, and what it was doing was electrospinning just above the surface. So you were able to have this like a focus point, and you get these tiny little spurts of very nice quality fibers from melt electrospinning. And this paper was so hard to publish. Yeah, it was back and forth, reject, and it was really, really difficult. And I think I remember at one stage, a reviewer said, "Oh, this looks like it's, you know, something out of the lab book, just thrown down." And I was like, "Oh, okay." So I actually wrote, "Yeah, okay, yes, you're right. There's very little about it. That's why it's important." And so, you know, this polymer journal, I think, has an impact factor of 3 or 4. So this paper published 10 years ago is 279 citations now, demonstrating that just because reviewers don't like your work, actually it's appreciated by people who work in the area. And this was the point of this, is actually try and wrap up all of the work in ARC and actually get it out there. And I feel as someone who receives public money to do research, it's actually our we should try and publish the things that we come up with. And so forth. We were able to start direct writing, and actually this is not done with an automated collector, it's done with the hands on an actually stole a Axis collector off a microscope on the weekend, unscrewed everything, put it underneath the electrospinner, and actually did this writing by hand, but you get beautiful fibers, and they were actually coloured depending on the diameter as well. And these were blends of these block copolymers and also PCL. And actually around this is the time where Dietmar and I were already communicating, and I said that would be a great thing to work together. It was also at a time that I had an opportunity to work in China. I did come to Singapore on a 2-week visit to help set things up in Singapore, but I think relatively soon after that, or around about that time, Dietmar came to QUT. I'd moved to Shanghai, and so we agreed to let's work together on actually making this like a proper sort of direct writing technology. We worked again. This is actually one of the old printers. Probably no one's really seen it. This is decommissioned many years ago. We had a syringe pump. We're blending polymers together, and actually Nicola Detta was visiting here. And you can see we have this metal box. There's no moving collector here. It's just static. And you still have the magnetic interlocks here to kind of stop the voltage from coming in. But a completely different system. But we could actually see as well that the fiber diameter was really dependent on the flow rate that we would deliver. And actually Nicola Detta was really important as well, because he was the first guy that sort of didn't listen to me and say, oh, okay, I work with the block copolymers and blend with PCL. I said, I'll just use PCL. Let's use straight PCL. And actually we found that was far more stable. And so instead of actually electrospinning, we started what I would call electrowriting, and actually doing direct deposition. And this resulted in the work of Toby Brown, and this was his first paper. And this is really the first time, I think, a paper was published showing that melt electrospinning could be used for direct writing very small fibers. And so the areas of additive manufacturing and electrospinning were coming together. Also the fact, and this is important, not the fact we can draw a straight fiber, because people have done that before in electrospinning, but actually to stack them up with some volume and height. More work by a postdoc at the time, Brooke Faruga, who was a postdoc of Tim, showing that when we're actually electrospinning these fibers and writing them in a certain pitch, the scaffolds that we would make were very much cell penetrating. This whole question about, is your scaffold able to be penetrated by cells? Is it cell invasive? Very clearly we were showing yes, they're fully being penetrated by cells, fully interconnected. And so this was an important paper. I think one of the things that kind of put it on the sort of scopes for many people was this paper, which was a really interesting physical effect that we saw, where if you have a scaffold, a melt electrolytic scaffold, and it's 93% porous, has a stiffness of about 15 kilopascals. And if you blend that, if you actually mix that with a matrix, so Gelma, which has a stiffness also of about 10, 15, or alginate, we're getting stiffnesses now about 250 kilopascals, so 54-fold increase in strength. So here is this stress strain curve for Gelma. For PCL, it's actually compressive measurements. You could actually see now we're getting close to cartilage, which was really crazy, because these fibers were both soft and flexible. They had a lot of porosity, and so we could now actually put cells under quite high mechanical loads without completely destroying your scaffolds. At the same time, FDM scaffolds, and I think here this is an FDM scaffold, this occupies a lot of space. So the porosity of this sort of the micro extruded or FDM scaffolds is a lot lower for melt electrospinning. And actually from this, a lot of fantastic papers are coming out. And this was really, I think, the time people are realizing that there's something in here. You know, you've got your hydrogel alone, and then you have your composites, and there's always this bar between them, showing that there's this massive strengthening effect by having melt electrospinning fibers. These are in straight lines, but also great example here of printing in sinusoidal structures, where you can create this the hydrogel alone. This is the composite. And the key thing is that there isn't a lot of polymer in the composite. There's not a lot of fibers. The percentage, the polymer volume is still quite low. So you didn't need to put a lot of this reinforcing polymer in there. We also did a little bit of work on that, but I actually want to talk about this paper for another reason. We were finding that we could, this is work in Würzburg, we actually printed a wall of PCL, and then on top of the wall we threw a fibre back and forth, oscillating, to kind of hold this down like a tent string so that it doesn't bend and buckle. But I want to highlight here that the ascending fibre and the descending fibre are positioned at a defined point away from the wall. And we found that this is very, very reproducible across multiple samples. So this, for example, depending on the wall height, the descending fibre would have a very defined landing spot. So even if something was on the surface already and we were doing melt electro writing, we were getting very, very reproducible structures coming from that. Another important part, because tubes are an essential part with tissue engineering, some work being done on the fabrication of tubular scaffolds, and this is mainly done through sort of winding at different angles. We didn't consider too much about where the fibres were going, we just wanted to create a certain pitch length. There's different approaches for heating as well. Heat gun. We used to use water circulators here, so actually have water going through a glass circulator, until we switched to electrical heating systems, and these are the heads that we have in Würzburg. You have electrical heaters here. This is how a lot of things are going. But I think, importantly, one aspect that has been done actually since 2006 is actually laser melt electrospinning, where you have a solid polymer stick and you feed it into a laser. And the faster you feed it into the laser, the faster the flow rate. And you can get nice structures from that. And the important thing here is that this is cold, this is not thermally degrading, and then it goes hot and then it goes cold again. So that thermal effect. And this is important when you want to get beyond PCL. I don't have a lot of time. I will talk a little bit about this, how we wrote this review because electrospinning and additive manufacturing was sort of converged, and there were other areas like near field electrospinning, which you had these structures, and also where you can actually create this single fibre jets. It actually got me reading this old paper by Geoffrey Taylor, and made me kind of realise that maybe my concept of electrospinning and what we were doing was a little bit wrong. This is from Taylor's paper from 1969, and you have water falling with no voltage applied, and it breaks into droplets due to the Rayleigh plateau instabilities. And so just before it breaks into droplets, there's a perturbation in the jet. It doesn't remain straight, it actually undergoes a bit of a... There's always perturbations. When you apply a voltage, you actually get a continuous jet. And you keep increasing the voltage, and then you get electrospinning. So there's a slightly different physical effect, and this paper from Taylor in 1969 actually was focused on this. So he was named after the Taylor cone with electrospinning, but when you read the article, he actually talked a bit more about this phenomenon, about how that happens. And this is, for me, the regime in which we try and operate it. Here we have this is a video. We have basically a fluid that's falling. And if we didn't have this voltage, this jet would break up. Yeah? And what happens is when you apply a voltage, you can actually stabilize this falling fluid at a low flow rate. This is an example where 6 kV, this is also from Taylor's paper, where at 6 kV you're still getting droplet breakup. You reach a threshold where suddenly you get this contiguous jet. Once you've achieved that, you can now drop down the voltage down to 4 kV. Here you're starting to get some droplet breakup. So the use of a voltage in our systems isn't to eject a jet like an electrospin, but it's there to prevent these kind of instabilities just before the droplet breakup. Because when you charge a fluid, all the charges go around the surface. And so it's now a very, very strong structure that doesn't undergo perturbations and doesn't go through droplet breakup. So in a way, the reason we apply voltages is to prevent droplet breakup. And there's recent papers showing that you can apply as little as 100 volt, 200 volt to a polymer solution and maintain this jetting phenomena. And that's one of the reasons that actually I switched calling it melt electrospinning writing to electro writing. Because for me, electrospinning is about the electrical instabilities, whipping just before the surface, and this is what we were doing before. And so that's how I've sort of changed terminology a little bit. And we find that MEW is applicable to many fluids, so polypropylene, polydioxane, or PVDF. This is a photo cross-linkable polymer, and also thermoplastic elastomer. So we tried a range of different fluids, different polymers, and they all seem to work as long as there's not too much thermal degradation. In fact, this is a recent paper where they call it 3D jet writing, where PLGA is dissolved in a very high concentration, I think within chloroform. And so you can actually do writing, and these are actual SEM images. So nice structures. The difference with melt electrospinning versus this 3D jet writing is that this box size is really large. Yeah, so this I think is about 1 millimeter in size. I think as they start going closer, they have more instabilities. But it's an interesting demonstration. Okay, I am talking too long. I knew I would. I have 2 hours, all right?
I call you Oliver.
So here's really where we are. Electrospinning, number of publications is quite significant. And when you look at melt electrospinning, it's just a fraction of what has been investigated. Within that, melt electrowriting is increasing. Actually, I don't have the data for this year, but I think we're about 20 or 25 publications this year. So it's increasing significantly because it does have that ability to place fibers where you want, and this changes a lot. Regarding the Gartner hype cycle, we're probably here. We're right at the bottom of that technology curve, and I think we have a lot of room for improvement, a lot of things to discover, and the next decade is going to be definitely exciting. Just to really kind of get an idea of how this field, I think, is going, it's good to look at the citation for this publication. It's cited by 308 people, but importantly, the first year was 9 people cited it, and this was a full year. So, you know, it basically gained interest, and so now we're actually going to be having the highest number of cites this year on this topic, and I think this is really the paper to kind of see how the whole field is tracking, because this is what people will be citing. For challenges in the future, thermal degradation is a big one. It's not a big issue with PCL. PCL is lovely, 60-degree melting point, hydrophobic, doesn't have a lot of water going into it, but PCL is not the only. It's a great material because it's useful for in vitro and in vivo, but there are other polymers out there that are also have different properties that you'd like to explore. Thermal degradation is a big issue with most of them. Scale up, and also the accessibility, and I mean that by how can others access this technology? Yeah, I mean it's fine that we can have our printers here and that's all good, but actually we should be wanting others to also jump on the boat and actually also discover things, because ultimately we're trying to do things for improving medical health. So, you know, allowing people to purchase printers, quality printers, rent time on printers or scaffolds, software that allows anyone to work in a machine and design, and everyone doesn't have to learn G-code beforehand, and also placing fibers together. But this is a recent work done with a laser. Again, within 10 seconds you can establish a nice jet. And here you have a cold filament, and this is hot now, and this is cool down. And this may allow us to be able to work with polymers as difficult, such as polyglycolic acid, which degrades normally after 2 weeks in the body, and thermally degrades very, very quickly. We've tried to melt electrospin it, it's a mess. Probably even worse a mess than that old picture that I showed you. Scale-up is being dealt with. I mean, here you have the only not the only scale-up system, but actually maybe the only scale-up for MEW. There are melt electrospinning scale-up systems, but they don't direct write. And so you have this scale-up concept, which actually fabricates either large single sheets, or alternatively lots and lots of smaller scaffolds. This is essential for any development of this technology in the future. The number of printers are increasing. I'm kind of going to lose track of all of it soon and give up on this. But we have a focal point here in Brisbane where we have a lot of printers. We have 7 in Würzburg. And I think the US is now kind of realizing as well that this is something that is really important. And we've been a little bit lucky to be able to work in, not peace and quiet, but work without the attention and the larger money that the US has, but this will be coming. And you'll see some big developments in this area, I think, over the years. There's a few companies that are selling melt electro-writing printers. Their quality is a bit dubious. I'm really surprised at how willing they are just to sell stuff, irrespective of whether it works or not. I think they see it as like a research-based thing, and if there's a problem, you sort it out to the researchers. Quite a few unhappy people I've spoken to who have the printers and are frustrated that they can't print what we're able to print. But we've actually also been trying to be very sharing also with the technology. I think this is great to have a Jove video on how to do melt electro-writing for anyone who wants to learn. Erin, who is actually from QUT, was a BioFab student, she has looked at the mathematics of how to print controlled on tubes and has created this website that you can go to and you can actually generate on the website intuitively by the diameter that you want and the winding angle, and auto-generate G-code that then allows you to make the structure that you want. And this allows people who have printers, tubular printers, to use it, alternatively to kind of start getting more complex. And so this is a tube with 15 sort of pivot points along here. The spikes are due to the fibre sagging and looking inside the tube outwards. You can see this is the bottom fibre, there's a bit of embossing on here, and then you have this sagging, and it's interesting that you have this sort of spiky structure on the surface. Another paper Andre worked on is like sort of dimension-based design, where you, by changing the air pressure and the speed, and this is something also known here, you can change the diameter. But also turning this around a little bit and saying, well, the dimensions of what we make is something that is like a language that everyone can understand. Biologists, clinicians, physicists, engineers. We can talk about what size structure would you like. So I think this is an example. There's 5 microns to 30 microns in 5 micron increments. This is still smaller than anything that can be made with micro extrusion of polymer melts. So this is just demonstrates that sort of smaller scale structures that can be made. So really, it is as a platform, it is it's reliable and simple and it's repeatable. The manufacturing can be monitored. I didn't talk about this, but you can look at the jet. And for a set of conditions, the jet should be a certain angle, and a lot of work's been done on that here. It produces something new as well. It allows the ability to design microscale structures that are normally difficult. This is, for example, 3 millimeter tube, and so we're having guided structures in here. There is a path. I mean, no MEW product has gone through the regulatory process. However, other similar technologies have before us, such as fused deposition or micro extrusion and also melt processing. So that helps us. Has an ability to scale, and also interchangeable. Again, the fact that you can relate one head of one printer to another head of another printer, as demonstrated by Felix, is exciting. There's a few other things that we should be working on as well. Getting a community together, having conferences where we have sessions on this topic. And the great thing about being so early is we can actually decide what kind of community we want. Yeah? Do we want a friendly community? Do we want a community where you have equal men and women involved? I mean, this would be great, because so many other techniques, there are such a kind of skewed and weird environments. And also make the printers accessible. So just talking about people, Christina and Dirk were really instrumental. And actually, the whole period of MEW has just been built up by young people who are enthusiastic, willing to work and develop this, one after the other. And so these people helped me out in Aachen and also in Southampton. Nicola Detta, Fred, Toby Brown, also Tim and Dietmar here, really pushing this, and I'm not sure if you know Anthony Skelton. This is an example of what happens when you don't have a professional photo on your on the web. I'll find something and then I'll put it up there, and yeah, wizards welcome. And other people that maybe you sort of know or remember. So Brooke is here, Anna, Annika, Lourdes, Laura, Boris is actually now in Würzburg. Felix and Eleanor, really contributed a lot, and I think the important thing is to kind of keep on this whole, development and progress forward. Also in Würzburg, some lovely people in Würzburg working on this, addicted to the machines. They come in, they print something, run to the microscope, and they're working in the evening not because I tell them to, but because they just want to stay there because it's so much fun. So we have some great people, Andre and Motaz. It would be really good to try and get these guys a little bit, knowing the people here at QT further. And actually the biofab degree, I just want to finish up on this, has been really instrumental for not just doing projects, but MEW. MEW printer, Wollongong now has one, QT of course has one. So now we're throwing people back and forth, and we have people here, but all these people have had months and months of experience now, how to operate MEW printers, how to establish them, and then I think the biofab degree is really essential in not just having some training, but also putting young people, with ideas onto this. And you might see there's a gender difference, and that's awesome, yeah, because it would be great to not follow the same issues or the other paths that other technologies and fields have. And also coming along the idea of, are we a community that is friendly, sharing, open, dynamic? And I think some of these things we can actually impact on now. So with that, I'd definitely like to thank Dietmar, Tim, Felix and Eleanor. It's people here who have worked with over the years. Also Jürgen as well for believing in this, seeing that all there's potential. And importantly the EU and also German Research Foundation for also seeing that there's potential in this technology. So with that, thank you very much for listening, and I'm happy to answer any questions.
Thank you, Paul. That was awesome. Questions? Above.
Thanks, Paul. I have one question. Where do you see the future of Melt Electrospinning writing in 5 or 10 years? You mentioned that there's a future of
yeah, sure.
writing.
Am I permitted to be a bit arrogant? I think that this is what electrospinning was meant to have been. The ability to design, place, and control where every single fibre goes. And this promise of what electrospinning was giving many, many years ago, which hasn't really been seen through, either economically or through research and translating into actual products for people. I think this is really well positioned to kind of elbow this aside. I think in 5 to 10 years, MEW can be like a gorilla of a technology. Yeah, where particularly if many people can access it. Yeah, this is the benefit of solution electrospinning. You can set it up quickly, but is it possible to have relatively low-cost entry-level MEW systems? How can others do it? So yeah, I believe the future of MEW is incredibly strong because there's also a fundamental platform upon which to base it on, where there is a path to, if you can demonstrate that your product beats a gold standard that's currently in the clinic by a certain amount, then you have the opportunity to then translate this and actually then be used. So yeah, I think in 5-10 years there will be MEW conferences, like there are electrospinning conferences, but they will be far more interesting because the structures, and now it's about design. The thing about solution electrospinning, I started off in solution electrospinning. The first day in the lab is fantastic. Yeah, you come in and you set things up and you electrospin something and you've got nanofibers. It's brilliant, really, really good. The problem is like the next 3 years is exactly the same day, repeated over and over again. And that ability to design and not just kind of get what you want, you passively stand back as this, substrate is just blasted and created for you. The ability to design and think about what you want and how you can introduce the mechanics that you would like. And the porosities and also with the different materials. We haven't even started exploring, what does melt electro-written PEEK feel like? Yeah, polyether ketone, high strength polymers. Yeah, so this is all areas to be discovered. And one of the reasons I'm also very open about this technology is there's literally so much to do. Yeah, it's overwhelming. Part of the challenge is like, okay, I could do this, this. 30 different projects I could line up right now. But I have like 5 students, so okay, I have to focus them on something. And so I'm very, very positive about the future. And maybe coming in, to you this kind of seems normal, we have this 3D printing technology, etc. You guys are in a special location. Yeah? There's no other lab in the world that has such equipment at your disposal. And I know that there are other labs out there that are incredibly jealous. They would love to have their hands on one printer and do work and investigate. So, I would definitely go ahead with a lot of confidence and also believe that you are able to make an impact. Yeah, we started things off, but we're not at the machines. We can't innovate, we can't observe, we can't see. And so I think there's so many rooms for all of you working in MEW to forge a career path that's distinct. And yeah, so that's me being a bit arrogant about the technique, which I can because I'm in Australia. In Germany, it's a bit difficult to say such strong things. But I think it's the future is incredibly bright.
Wow, okay. I almost wanted to end here, but Tim, go ahead.
If you could provide us a very quick answer to alternatives to the XY stack. They're pretty clunky. There's got to be better alternatives.
Yeah, XY. You have different axis robot systems available. Freeform writing, both collector, head, dome printing. I think that's going to be the future, sort of freeform writing on complex surfaces. The other thing that's important is to try and build up with height, with accuracy. Go to the centimetre level where you're still putting fibres where you want to, and then controlling that. So maybe auxiliary electric fields as well if become important. Was I kind of accurate?
Yeah.
Because I think when you give these kind of talks, you're like summarising history, and you think, well, I think it was this way. No?
Yeah.
But you see, I think the important thing is that evolution of solution electrospinning, why people were doing it, that focus on nano and this kind of push into this area. But then not literally seeing what's happening in front of your eyes, that these are not scaffolds, these are not cell-penetrable materials that you're making. And I think the easiest person to fool is yourself. I think Richard Feynman, that's a quote of his. So yeah, look, see what you have. Always notice stuff happening in the lab. If we were running through the SEMs back in 2003, we're looking mess, and we didn't observe in one corner of one sample, and we had about 20 samples we ran through. With these beautiful little fibres. If we didn't see that, if we didn't observe that, if we weren't thinking about going home and, okay, let's call it a day, we've done 15 samples, the rest are going to be awful. No, you have to notice, you have to pay attention and observe, and that gets you stuff. And if I just finish on one thing, because I do get asked a lot by young people about what should I do. I should do this, should I do this? And my suggestion to them, it doesn't actually matter what you do. You just do it well. Yeah? And everything follows from that. Yeah? I had no intention of working in electrospinning until someone said, oh, do you want to do something in it? Sure, let's do that. Projects aren't working, but instead of giving up, rack your brain. How do I get around this? How do I get around the problem? What was really the meaning of the challenge thrown down? How can I strip that to a basic level, change something, and then build it up, because you can end up somewhere else. That's important. So yeah, definitely take life in your own hands. Don't worry about what specifically you're doing. Just be really good at it.
Good. think this is wonderful to end here. Let's thank Paul again for a wonderful talk.